Hey everyone, one of the major reasons that people are not using the fixed line transit systems is that it often fails to provide end-to-end transit. We have to go to a bus stop to get on the bus, and from again after getting off the bus at a particular stop, we have to travel to our destination. Now, these parts of the trip, we refer to them as the first and the last mile. One way to solve this problem is to create a system that integrate the fixed line transit systems and also a mobility on demand service, for example, a shuttle service or a taxi service that provide the first and last mile coverage. The benefit of integrating these two systems is that we are not really extending the capacity and the coverage of the fixed line transit system, but we also try to minimize the total mileage is mobility on demand vehicles as compared to their operating on their own. So this gives rise to the first and last mile problem, in which we are given information about the fixed line transit system, the frequencies and the routes, and also the information about the mobility on demand vehicles, their current location, the capacity, where they are headed. Of course, we have the information about the demand in terms of origin and the destination. And then we try to serve this demand uh, using both the fixed system and the mobility on demand vehicles, such a way that we try to achieve some goal. In our case, we try to do it while minimizing the mileage we put on these vehicles. So we have a few assumptions. Since this is a real-time problem, we have to solve this problem in batches. So we will batch request, for example, 30 seconds, and then solve this optimization problem. And also we ignore the capacities of buses due to two reasons. One is often the buses are underutilized, and also the capacity of the buses are much more flexible compared to the mobility on demand vehicles. People can travel in a bus without a seat, and also in a single iteration we assign a vehicle only one passenger. Let me explain the framework that we use to tackle the last mile problem. So we are given the information about the requests, the buses and the shuttles. The first thing we do is, for each passenger request, we generate a list of buses that can serve a part of the passenger request. Theoretically, this list can be long, as any bus can, and a combination of bus can be fit into this list. But however, in practice, due to time constraints such as the limit on the total trip duration, this list is much shorter. Next thing we do is, after identify all these bus scenarios, is that for each scenario we try to identify the first and last mile travel requirements. The first mile travel requirement will be specified by the location of the origin of the passenger, the time that the passenger can leave the origin, the bus stop location, and also the deadline in which the passenger has to travel to the bus stop. Similarly, for the last mile, we have the location of the bus stop, the time that the passenger get off from the bus, and the destination, and also the deadline to reach the destination. Once we have identified all this information, we can build a graph in which the first column represents the passenger request, and the second column represents all the identified first and last mile trips, and the third and the final column representing the shuttles. So we can add an edge between a shuttle and a first or last mile trip if this shuttle can serve that trip within given time constraints. And if so, we will represent the cost of the trip as the edge weight. In our case, a cost of a trip is the added mileage on the shuttle to serve this particular trip. So once we have this graph, we have all the information to solve the assignment problem, which is solved via an ILP. So once we have solved this problem, for each passenger, we have the identified a bus or a combination of buses, and also the first mile and the shuttle that serve that first mile, also similarly for the last mile. To evaluate the performance of the proposed framework, we conduct the following experiment. So for this experiment, we have selected the Chattanooga area and we have generated about 92,000 requests. These requests represent the commute in the morning to the workplace and also the return trip in the evening. These trips are generated based on the US Census survey. As you can see, we only have demand in the uh, morning and also in the evening. In the morning, it is from 7 to 9, and in the evening, it is from 4 to 6. And during these demand times, we have about 400 requests coming in every minute. So we simulated the request, the fixed line public transit, and a fleet of mobility on demand vehicles having 4,000 vehicles of capacity 4 while solving the optimization problem via the proposed framework. On average, it takes about 90 seconds to solve one cycle of the optimization problem. This demonstrates that we can use this real-time application, especially because we can further reduce the execution time as we can parallelize most part of the framework. In terms of the trip composition, about 75% of the trips does not use buses. They are directly served by mobility on demand vehicles, and about 74% of the trips use both buses and mobility on demand vehicles. Overall, we save about 4% in the vehicle miles travel of all the vehicles compared with the scenario where we don't have the fixed line transit system. However, further gain in the reduction of the vehicle miles travel is limited by the fact that only about 24% of the trips can use buses, at least to serve some part of the trip. This is due to the fact that if you can see the figure on the left, only a small portion of the area is served by a fixed line transit system. But if you can see the figure on the right in our simulation, you can see the requests are more distributed than the small part of the area that is served by the transit system.